Welcome to all of you. Today we are going to discuss about the basic principle of the NMR spectroscopy. And to understand the basic principle of NMR spectroscopy, we can consider any organic compound that contains the hydrogen. For example, say we consider the acetic acid. And initially when our compound is not subjected to the any external magnetic field, then all the hydrogen nucleus or simply the proton are in the random orientation, or we can represent them as where these arrows represent the net magnetic moment of the individual proton. Now since proton has some spin and charge, so the individual proton always associated with some magnetic moment with them. But the point is that in the sample, due to the random orientation of the proton, the magnetic moment of all the proton get cancelled out by each other. So all the proton experience the same amount of the energy, and consequently all the proton belonging to the same energy state. So we can represent them as all these nuclei initially they belonging to the same energy state, and that state is called degenerate energy state, and that state is called the degenerate energy state. And now point is that due to the some magnetic moment associated with the proton, it can behave as a tiny magnet. So in the diagrammatically we can represent the proton with some net magnetic moment in this direction. This can be treated as a tiny magnet. Now when the sample when our compound is subjected to the external magnetic line of forces, or simply the external magnet, in the influence of the external magnet, then what happens? Then our proton as wobble precession, or simply the spinning top like precession will start, and that is called the Larmor precession. And in that case what happened, say initially this is the direction of net magnetic moment of the proton, and at the other time this is the net direction of the magnetic moment, or simply we can say that the direction of net magnetic moment is continuously changing. Or in the Larmor precession what happened, there is a continuously change in the direction of the rotational axis as well as change in the spin. The spinning as well as the change in the rotational axis take place simultaneously, and on an average the net magnetic moment is going to be in this direction. Here is this on an average. So this is the net direction of magnetic moment in Larmor precession. And in the presence of the external magnetic field, say this is the magnetic line of forces for the external magnet, then there will be two possibility. Then there will be the two possibility. Either the proton that undergo the wobble precession or the Larmor precession, it has some magnetic moment in the direction of the magnetic line of forces, or the magnetic line of forces can be opposed by the proton. simply the magnetic moment of the proton is in the against the direction magnetic line of forces, and that state will be the beta state. And the state in which the magnetic line of forces and the magnetic moment of the proton is in the same direction, that state will be the alpha state. And corresponding to the alpha state, the spin quantum number will be the plus half, because in the alpha state the proton is precise with the clockwise direction, but in case of the beta state the proton precessing in the anti-clockwise direction. And the frequency associated with these kind of a precession is the Larmor precession. And this type of the two state of the nuclei is called the spin isomer. These are called the spin isomers. So these are the two possibilities that can happen for the nuclei under the influence of the external magnet. Now if we try to represent the energy versus the applied magnetic field strength, then we will get this situation in which initially when we do not apply any external magnetic field, then all the protons in the sample are in the random orientation, and from this point we start increasing the magnetic field strength. Then if we increases the strength of the magnetic field, then the alpha state will going to stabilized and the beta state will going to be the destabilized, because since the proton can serve as a tiny magnet, so and from the external source we apply the external magnetic field, then the say here is the north pole, here is the south pole, and here is the north pole, here is the south pole of the external magnet, then the opposite pole going to attract for the alpha state of the situation. So the alpha state will be attracted by the external magnet, but at the same time the beta state which can be represented by the south to north, then its magnetic moment will be repelled. So the net magnetic moment of this kind of the tiny magnet in the beta state for the proton is repelled by the external magnetic line of the forces. So this will be the unstable situation for the nuclei. And so definitely the proton prefer the alpha state, because in this situation the proton have the lesser energy, and that is the case for the lower temperature. But most of the time we analyze our sample at the room temperature, so the previous figure will going to be replaced by this one, because the point is that the energy difference between the alpha and the beta state of the nuclei at the magnetic field strength of the 1.41 Tesla is about 2.39 into 10 raised to the power minus 5 kilojoule per mole, and the thermal energy that is available from the room temperature is about 2.477 kilojoule per mole, and which is significant enough to populate the beta state also for the nuclei. So initially we have the magnetic field is 0 strength, and if we try to increase, then the energy state is going to increases, energy separation is going to increases, and when we stay at some constant magnetic field strength, then it remains a constant, but the thermal energy will populate both these level of the alpha state and the beta state. although at the room temperature roughly about half of population of nuclei gets sufficient energy to stay in the beta state due to the thermal energy, but there will be some population in the ground state in excess as compared to that of the beta state, and that population is called the excess population. For example, you have 1,000,006 protons in the alpha state, and in the beta state we have the 1,000,000 protons. Then excess population will be equal to n alpha minus n beta, which is came out to be the 1,000,006 proton minus 1,000,000 proton is equal to the 6 proton. These proton will be called as an excess population, and these excess population will be responsible to do the nuclear magnetic resonance phenomena, and which is finally responsible to make the NMR spectrum. When you expose your compound, which is already placed in the external magnetic field, to the electromagnetic radiation of the radio wave type, then out of these excess population, say 6 proton in the alpha state, then as soon as the frequency of the incident radio wave exactly matches with the Larmor precession frequency of the proton, then the nuclear magnetic resonance will occur for the particular type of the proton, and it will flip its spin from the alpha to beta state, and when it returns from the beta to alpha state, then it emits some electromagnetic radiation, which is going to be detected by the detector and give the corresponding NMR signal. And this situation can be depicted by this figure. Here you can clearly see that when you expose your compound to the external magnetic field strength, then it undergoes the Larmor precession, and when your compound is in the presence of the external magnetic field strength, and then you expose your compound to the electromagnetic radiation of the radio wave type, then these nuclei absorb these electromagnetic radiation only if the frequency of incident electromagnetic radiation and that of the Larmor precessional frequency of the hydrogen nucleus is going to be the exactly same. Only then these electromagnetic radiation is going to absorb by this hydrogen nucleus, and it will flip its spin from alpha to beta state, and beta state is of the higher energy, and when it returns from the higher energy state beta state to the alpha state, it emits some electromagnetic radiation, which is to be detected by the detector and give the corresponding NMR signal. So this is the general phenomena for the absorption of the electromagnetic radiation of the radio wave type by the nuclei. And the expression for the energy for the corresponding spin state ms will be given by the EMS is equal to minus G mu B B naught ms, where G is the proportionality constant and mu B is the nuclear magnetic moment, and B naught is the applied magnetic field strength, and ms is the spin quantum number, and the value of ms is plus half for alpha state and minus half for beta state. Alpha state is for the clockwise and it is for the anti-clockwise. So now in this figure, so the energy separation between alpha and beta state is the E minus R, which is corresponding to the high energy state beta state, minus energy corresponding to the alpha state. So minus mu, put this minus half into this ms, g mu v b naught, and ms has a minus half for the higher energy state, and minus of minus g mu b b naught, and ms is plus half. So we will get g mu b b naught minus minus plus divided by 2 minus minus plus g mu b b naught divided by 2. So overall it comes out to g mu b b naught. So delta E is equal to, which is equal to h mu is equal to g mu b b naught. So which can be rearranged as mu g mu b b naught by h. And in this expression, the mu is the frequency which is required for the proton to resonate from the alpha to the beta state. So this is the frequency requirement of the radio wave by the hydrogen nucleus. And also it is important to note that the NMR spectroscopy is not applicable to all the nuclei. It is only applicable to the it is only applicable to those nuclei which have odd protons or odd neutrons or odd protons and odd neutrons separately. For example, hydrogen 1, carbon 13 and fluorine 19, phosphorus 31, and the corresponding proton are 1, 6, 9, 15, and corresponding neutron are 0, 7, 10, 16. And in these nuclei you can clearly see that it have the odd proton, this have odd neutron, this have odd proton, this have odd proton. So in these nuclei they have either the odd proton or odd neutron. So these nuclei are the NMR active nuclei. These nuclei are NMR active nuclei. And these conditions are requirement for the NMR active nuclei, because these kind of the nuclei have the quantized spin angular momentum and the magnetic moment. So that's why these kind of nuclei are the NMR active nuclei. And also you can consider in nuclei carbon 12, 6, 6, and this nuclei doesn't have the odd proton or the odd neutron. That's why this nuclei is NMR inactive. This nuclei will be the NMR inactive. And in the next video we will talk about the chemical shift and factor affecting chemical shift. Thank you for watching.